All right, hello everyone. Professor Ostanek here for ENGT509. Today we're going to be talking about Cramer's rule. Cramer's rule is a method of solving a system of linear equations having n equations, that's our number of rows, and n unknowns, that's the number of x's or the number of columns. Should be familiar with this. And if we write out an example problem here, we've got three equations and three unknowns, x1, x2, and x3. We can represent this system of equations in matrix form. The coefficient matrix A is shown here, 2, 3, minus 4, where we're pulling these coefficients directly down into our matrix A. And the column vector B, it would be 3, 1, and 2. So A is a matrix, X is a column vector, those are our unknowns, and B, the right-hand side, is also a column vector. So again, just to quickly review the subscript numbers here, the first one is the row, and the second one is the column. So you can see row 1, row 2, all the way down to row n, and column 1, 2, and n. Okay. Again, you've solved these systems of equations before using this method where you invert the matrix A and multiply by the column vector B. In this case, the solution is shown here. x1 is minus 5.0476, x2 and x3. So here's the key with Cramer's rule. Again, it is a method of solving a system of linear equations. But the difference is that Cramer's rule allows you to solve for one of the unknowns at a time. You don't have to solve for all three simultaneously like you do when you invert A and multiply by the column vector B. Here we got all three values at the same time. With Cramer's rule, you can solve for any one unknown that you're interested in. The formal definition is shown here. The ith unknown is equal to the determinant of matrix A sub I divided by the determinant of the original coefficient matrix A. So this A sub I, it is the coefficient matrix, but you replace the ith column with the column vector B. I'll show you that on the next slide, but first, quick and important note, Cramer's rule is only applicable when determinant of A is non-zero, because if this were 0, then all of our unknowns would be infinite and this wouldn't work. So jumping back to our example problem here, the same three equations and three unknowns we had, if we're interested in, let's just say we're interested in the first unknown, x1, our I is equal to 1. So to construct this matrix AI, in this case it would be A1, we're going to replace the ith column, or the first column. You can see these coefficients, 2, 1, and negative 2, have been replaced by the column vector B. Now that we have A1, we can solve for x1. It's the determinant of A1 divided by the determinant of A. So let's go ahead and jump over to MATLAB and take a look at this. Okay. So I've got our original matrix A and the original matrix B shown here. And real quick, let's go ahead and solve this using, the inverse of matrix A times our column vector B and take a look at what we get. Okay, that is exactly what I showed on the PowerPoint slides. So now let's solve for each one of these individually, x1, x2, and x3, using Cramer's rule. So to solve for x1, we need to create a new matrix, A1, and we're going to replace the first column with our right-hand side, the B vector. So to do that, I can simply write B, and now I'm going to write comma to separate the first column is 3, 1, 2, and I'm going to fill in the remaining two columns. So I need all of the rows of each of these two columns. So I type A open parenthesis, semicolon. That'll give me all my rows, but I only need the second and third columns. So the syntax for that would be to write 2 semicolon 3. And let's finish our square brackets there and make sure this worked. Okay, yep, looks good. I can see that my first column has been replaced with B, and everything else is kept from our A matrix. All right, great. Now we can solve for x1 using determinant of A1 divided by determinant of A. And there we go, it worked out. Perfect. Let's do x2. All right, oh, sorry, look, we're gonna do x2, but we need to put together the A2 matrix. All right, so now going back to our original coefficient matrix A, we need the first row. Okay, let's do that. So A, yes, I need all of the rows, but only the first column, okay? And I need my column B, and then I need to pull out this last column here. All right, let's make sure that worked. 2, 1, -2, yep. 3, 6, -1 has been replaced. Looks good. And then -4, 1, and 3. Okay, everything looks good. Now we can type out x2 equals determinant of A2 divided by determinant of A. 1.3810, yep, that matches. Looks good. All right, let's do the last one. A3 equals A, all of the rows, but only columns 1 and 2, and then our B column vector. 2, 1, -2, 3, 6, 1. Yep, that looks good. And then we've got 3, 1, 2. Yep, this all looks good. x3 equals determinant A3 divided by determinant of A. Let's double check, -2.2381. There we go. Everything checks out.